Cool. So last time we introduced our main theorem, which is our Jordan decomposition. So if you have any matrix A, so theorem, this is my Jordan decomposition. Given any complex matrix, square matrix, complex square matrix, we can write A as, well, some change of basis. And then instead of a diagonal matrix, it's nice when you can diagonalize. And some matrices you can diagonalize, but as you saw last time, you can't always diagonalize. So this is kind of the next best thing where we say, well, we can get an almost diagonal matrix. Well, that almost diagonal matrix is called J, where J is some matrix made up of these Jordan blocks. So some first block of size K1 with entries lambda 1 down through some final Jordan block of size Km with entries lambda m, where each block, let's say jk of lambda, is a k by k matrix with lambdas along the diagonal and ones directly above the lambdas and zeros everywhere else, where this is a k by k matrix. And we said, and we saw last time actually, there's an algorithm that gives us what these blocks are. And since there's an algorithm that tells us what the blocks are, that means that your J is unique up to reordering the blocks. So let me just remind you a little bit about the example we were looking at last class to make it very concrete. We have this matrix A, which is a 3 by 3 matrix with entries, let me make sure I get this right. One, negative 1, 2, negative 1, negative 1, 4, negative 1, negative 2, 5. And we saw that this matrix has eigenvalues 1 and 2. And if that's all you knew about the matrix, well, it will give you a number of possibilities for what J could be. Because here these J, since the lambdas along the diagonal in the upper triangular matrices, your lambda are just your eigenvalues. So you're like, okay, this is made up of some Jordan blocks with eigenvalues 1 or 2. So you're like, there's a few possibilities. Your J might be something like a 2 by 2 block of 1s. So that would be something like that, yeah. And then maybe a 1 by 1 block of 2s. So you might think it's something like this. Or it could be something like maybe a 1 by 1 block of 1s and a 2 by 2 blocks of 2s. So just to make it explicit, here is my 2 by 2 block of 1s, my 1 by 1 block of 2s. Here is my 1 by 1 block of 1s, my 2 by 2 block of 2s, right? Or it could be something else, right? It could be, I don't know, it could be something like a 1 by 1 block of 1s, a 1 by 1 block of 1s, a 1 by 1 block of 2s. Or, okay, there's one or two other possibilities we didn't do. It could be a 1 by 1 block of 1s, a 2 by 2 block of 2s, a 1 by 1 block of 2s, and a 1 by 1 block of 2s. So here I had 3 1 by 1 blocks. So there's lots of possibilities for what this matrix might look like. And so what we needed was some way to know, like, how many blocks are there of each size? How many 1 by 1 blocks are there of 1s? How many 2 by 2 blocks are there of 1s? How many 1 by 1 blocks are there of 2s? How many 2 by 2 blocks are there of 2s? And so we saw an algorithm to give us that, calculating these gamma values. And that told us that this is the correct J. Up to reordering. So you could also have first your 2 by 2 block of 2s and then your 1 by 1 block of 1. So we saw that last time. But since there is some algorithm that specifies what this is, and you know the values are just your eigenvalues, you now know, okay, this J is going to be determined by whatever matrix A is. And so we have an immediate corollary of this. Since your J is unique, a corollary of this theorem is that two matrices A and B are similar Is there an extra I after the L? Similar? That doesn't make sense. A lot of vowels going on in that word, huh? Two matrices are similar if and only if A and B have the same Jordan form, sometimes called the Jordan canonical form. Jordan form J. Canonical because there's a unique one up to this reordering. So again, this is always when I say it's unique, I'm saying up to reordering of your Jordan blocks. Okay, so I want to prove this, show that this really is equivalent, but think about what this is saying. This is saying if you want to know two matrices are similar, instead of going out like, what do I mean two matrices are similar, right? Like, let's remind ourselves what that means. That means that I can write A as some change of basis, and then it's B, right? Like, do some change of basis matrix, and A becomes B, right? So some change of basis matrix, say C, there exists some matrix C, so you can write it like this, right? Some invertible change of basis matrix C. That's what it means to be similar. And so being similar means, well, one linear transformation is really equivalent to another one up to changing your basis, right? Okay, so if you want to know if two matrices are similar, which maybe is kind of a hard question to ask, like how do I know if there's essential C or not, right? Well, the answer is you can just find the corresponding Jordan form for A, like we did last time. Find the corresponding Jordan form for B, like we showed how to do last time. And then just see, like, do you get the same Jordan form for each of them? And if they're the same, now you know matrices are similar. Does that make sense? So this gives a very nice test. And in the fact that it goes both ways, there's no worrying about, well, maybe sometimes there'll be cases where, like, no, it's an if and only if, right? If they have the same Jordan form, they're similar. If they're similar, they have the same Jordan form up to reordering your blocks. So really, you just need to calculate your gamma values that we talked about last time for these guys. Okay, so let's prove this. Let's prove this. And this is one of these proofs where you really just unpack the definition, right? We really just need to kind of follow our nose and see, where it leads us. So I guess we can go the down direction. Here we're given that A is some BC B inverse. These are all square matrices, right? So I didn't say it, but A and B are, square matrices, and so we can talk about this Jordan form. So I guess I should have said A and B are square matrices. These get uploaded to YouTube, and then people come in the comments and they're like, you didn't say they were square matrices. And it's like, come on, I'm giving you free content, guys, right? Anyway, I appreciate those. Okay, so we're given A equals CB inverse. And so how do we get to say that A and B have the same Jordan form? Well, we know by a theorem that they each can be written as some kind of Jordan decomposition. So we can write A as, some PJ P inverse. But since we're about to do the same thing for B, let me just call this like P1, J1, and P1 here. And then B I'll write as P2, J2, P2 inverse, right? And so what do I need to show now? Well, I need to show that J1 and J2 are equal to each other up to some reordering, right, of your Jordan blocks. Okay, any thoughts? How can we do this? Well, I guess we just kind of string together what we have, right? It's just like we put down all the facts, now let's put it together. I know A is secretly of this form, so I could say, I could also instead write A as C, B, C inverse. But what is B? B is this guy, so it's really C, P2, J2, P2 inverse, C inverse. And so what is that? Well, that's secretly CP2 times J2 times CP2 inverse. And this is a Jordan decomposition for A, right? Where you have some Jordan canonical form in the middle. But I have another Jordan decomposition for A up here. And by the uniqueness part of the theorem, therefore, your J1 must be equal to your J2 up to reordering. Okay, so these are these proofs that write themselves. You jump back to the definition, and then you just, play around with what you have. Let's go the other direction. It's the same thing. So if I'm given two matrices that have the same Jordan form, so let's see what we're given. We're saying that we can write A as some Pj, P inverse, and I can write B as some, okay, well, maybe it's not P anymore, so I could do P1 and P2, maybe let's call it Q, Qj, Q inverse. But the point is they both have the same Jordan form, so they both have the same J. They both have the same J. Now I want to argue that A and B are similar. So it's like, well, how can I go from here to here? Thoughts? Yeah? Oh yeah, you could rewrite both in terms of J and then set them equal to each other. And sure, I mean, I guess I was going to try and bypass that, but that's a fine way to do it. So this gives you that P inverse AP is equal to J, but that's also equal to Q inverse BQ. And then that gives you, solve for your A equals multiply on the left by P, so P Q inverse, BQ multiply on the right by a P inverse. So I moved over the P inverse that was here as P, and I moved over the P as P inverse, and then you just look and you're like, that's just PQ inverse times B times PQ inverse inverse, right? Okay, so these are proofs that, like I said, just write themselves. So our corollary is that two matrices are similar if and only if they have the same Jordan form. So what is this really saying? It's saying like the Jordan form is capturing information about a matrix that is the same up to similarity, right? And so you might think like the Jordan form is kind of capturing like that essence of the linear transformation that's true across all different bases, right? So that's what this is really saying. If you're familiar with thinking about invariants, often talk about invariants, like what invariants stay the same under different linear transformations. That's really what this theorem is talking about. What invariants stay the same under various transformations. This is saying the Jordan form is like the essential thing that stays the same up to similarity. So really, really nice result there. But I want to go back to our main theorem because we never finished proving it last time. I introduced the theorem last time, and I gave an argument for why we have uniqueness, but we never proved it because although I showed you how to calculate J, I was assuming you had such a decomposition in order to get J, and And we never talked about like, how do you get P, right? Like if you actually want to write some Jordan decomposition, we also need to understand how to write P. And so today's goal is going to be trying to understand how we calculate the matrix P, so that now if I give you a matrix, you can actually find its Jordan form. In some sense, like J is the most interesting part of it, but P is relevant as well, and it's going to introduce some nice ideas for us. So here we go. How do we calculate P? So how to calculate this change of basis matrix P. And to calculate that change of basis matrix, what we want to do is we first just want to think, okay, let's just think about a really simple case where your J is just a single Jordan block. Right? So to begin, let's just, oftentimes in math when you want to understand something, you should begin with a really simple toy example. So let's just consider J to be a single Jordan block. Some k by k Jordan block of entries lambda. Now, once we understand this, we can just string them together, right? Because a Jordan form is just made up of lots of these blocks. And so if we can understand P for a single block, then we can be like, okay, now we can understand it for the whole matrix by stringing this idea together, right? But let's just think about this toy case right now. So if you have a single guy, then we're trying to say, okay, I want to understand like what this Pj does. I want to understand like what P has to be so that this is true. And so what we're going to do is I'm going to say, okay, we want to understand P. So we want to understand, so we want to end up with, we want to have A equal to Pj, where J is just a single Jordan block, P inverse. And so I'm going to begin by saying, say P is some matrix with columns. Column V1 through column Vk. So in a few minutes, I'll say some comments on why I use my notation slightly different than before, but let's just denote these as the columns of P. Then notice A times the first column of P. Let's think about what that gives us. A can be written in Jordan form as Pj, P inverse, times the first column of P. And so like here we need to think a little bit. Like what's going to happen when I have P inverse times the first column of P? What does that give me? So maybe we just need a little aside. Well, I know that P inverse times P is identity matrix, yeah? So that means that if I do P inverse times the entire matrix, V1 all the way over to Vk, that will give me this matrix where the first column is 1, 0, 0, 0, all the way over to the last column, 0, 0, 0, 1. But right now, we're just thinking about this first column. And so it's like, what is P times this first column? Well, the first row times the first column gives me 1. The second row times the first column gives me 0, and so forth. So that if I do the entire P inverse times this column, I'm just recovering the first column here. Right? So P inverse times the first column of P is just going to recover the first elementary vector. I'm going to call this vector E1. So this is just Pj E1. Are we happy about that? This is true in general. Whenever you have an inverse of a matrix times the first column of a matrix, it recovers the first elementary vector. And this kind of makes sense because like, what is the first column of your matrix? Well, it's what P does to E1. So inverse is taking you back to E1, right? Now let's think, what is J times E1? Well, I said J is just a block. So this is going to be something of the form whatever lambda is, and then it's like a 1 in a lambda and a 1 in a lambda, and so forth until you get down to your bottom lambda, and zeros everywhere else. So what is E1 times J? Just lambda, right? You just times this by 1, 0, 0. You just multiply down, you get lambda. Lambda plus a bunch of zeros. So this is really just P times, this just comes out, well, it's not just lambda, it's lambda with a bunch of zeros, right? It's lambda 0, 0, 0, 0. So this is P times lambda with zeros all the way down. So this is lambda times E1. Right? This is just lambda times PE1. And PE1 is just going to cover the first column of P. So this is just lambda V1. So what is V1? It's like, well, V1 is an eigenvector for A. Right? So where's my V1? Right here. This V1 was just an eigenvector for A. Makes sense because this first column is just like if it was just lambdas along the diagonal, and you'd have diagonal matrix, so you'd have eigenvectors corresponding to it. Now, the later entries, we might expect to be a little bit different because you don't just have lambdas, you have this a 1 and a lambda. And so it's going to change things a little bit, right? Like let's think about if we move on to like the second A times V2, like what is A times the second guy? The story is going to be slightly different. Like this is all going to be the same. This will just be E2, right? So it's just going to be Pj, P inverse of V2, which gives you an E2. And then that's just going to recover the second row of J, but second column of J, but now the second column of J is no longer just a lambda in the second position, it's a 1 followed by a lambda, and then zeros. So this is like a little bit different. And like let's think about what that then gives us. P times that will give you 1 copy of the first column of P, so 1 copy of V1 plus lambda copies of the second column, lambda V2, right? So lambda V2 isn't quite an eigenvector of A because you ended up with this extra piece. And that will just keep happening for the rest of it, right? So if I want to know in general what is like A Vj, I can just be like, okay, I'm going to do it with the jth guy, where here I'm thinking of j as being some value that's at least 2. It's different for 1, but at least 2 up until the last one, up until k. And it'll just be exactly like before. It's just p, j, and now it's the jth elementary vector, which was give you p, j, and then you're like, well, this is going to be the one that has a lambda in the jth position, a 1 above it, and then zeros everywhere else, right? Zeros everywhere else. All the way up here, zeros everywhere else, right? But there's a lambda in the jth position. And so when you multiply that out, sorry, this is just p times that. So when you multiply that out, you get lambda copies of Vj plus 1 copy of the guy before it. So you get 1 copy of the vector j minus 1 plus lambda copies of the vector Vj. Good? Now, over here, being an eigenvalue is the same thing as saying that if I move this to the left and pull out the v1, that I have a minus lambda I times v1 is the 0 vector. Okay? I move this guy over. There's now an identity matrix. I pull out the v1. It's a minus lambda I times your v1 is 0. But here the story is a little bit different, isn't it? If I move this piece over to the left and factor out v2, I get a minus lambda I times the vector v2 is equal to what? Just v1. That's what's left on the right-hand side. And in general, that's what happens. That a minus lambda I times vj should just give you the previous guy, vj minus 1. So let's draw a little picture of what's going on here. One way to think about this is v1 is the vector that gets sent to 0 when you multiply by this matrix A minus lambda I. But v2 is the vector that gets sent to v1 when you multiply by the matrix A minus lambda I. And v3 is the vector that gets sent to v2 when you multiply by the matrix A minus lambda I, and so forth, for however many v's you have. This first one is an eigenvector, and then you have these other ones which are vectors being sent to whatever the eigenvector is, or the thing that was sent to the eigenvector, and so on and so forth. And so this now gives us a strategy to find your vectors in P. Well, we've only done it for a single Jordan block, but if you think about everything we talked about, if you have multiple Jordan blocks, it's like, well, for this Jordan block, the first two vectors you'll just find this way for the eigenvalue 1, and then like the third vector, you do the same process with the eigenvector 2. So you just string it together for your different eigenvectors. Different eigenvalues. So let's go back to our example and actually show how we can calculate P now. So our example was this matrix A, where we had 1, minus 1, minus 1, minus 1, minus 1, minus 2, 5, 4, and minus 2, I believe. Positive 2. Okay, there we go. And we saw that this has eigenvalues 1 and 2. And we already gave away last time that this Jordan form is going to end up looking like a 1-by-1 block with eigenvalue 1, and a 2-by-2 block with eigenvalue 2. So here are my blocks. And so when we go and we think about what our matrix P should look like what is P going to look like? Well, first we're going to do this process for the eigenvector 1, but it's like, well, we only have to find one vector for it, because there's only one column. So we're just going to find v1 for the eigenvector 1, and then we're going to do this process for this 2-by-2 block. So we're going to need to find two vectors, v1 and v2, for the eigenvector 2. And that'll give you then your matrix P. So like a lot of this matrix is just finding that first, these v1s are just eigenvectors, right? So it's like, what's an eigenvector that corresponds to like 1? Let's do 1 really fast. Well, when lambda equals 1, I think we mentioned this last time, but we can just recover it really fast. My matrix A minus lambda I becomes the matrix 0, minus 1, 2, minus 1, minus 2, 4, minus 1, minus 2, 4. So like what is a vector v1 here that sends us to 0? You know, I want this to be sent to the 0 the 0 vector. So what should my v1 be?
0, 2, 1.
0, 2, 1 works. Great. So my v1 is 0, 2, 1. And we don't have to worry about going any higher in this chain because there's only a single, it's a 1 by 1 block, so there's just a single vector that corresponds to it. So there's the first column of P. Now if I go to the second and third columns, for these columns, I'm now looking for the eigenvalue 2, which gives me now my matrix A minus lambda I comes out to be the matrix -1, -1, 2, -1, -3, 4, -1, -2, 3. And again, I'm trying to figure out, okay, so what should my vector v be here? You know, what should this v be? What should this guy be so that it comes out to be the 0? So what should that be? What will satisfy as an eigenvector for this guy?
1, 1, 1.
Yeah, you could do 1, 1, 1. Yeah, that's great, 1, 1, 1. If you scale it and you say 2, 2, 2 or whatever, that's also fine. But now we have that v1, 1 is just the vector 1, 1, 1. So how do I find this guy? I mean, this is kind of the more interesting one. It's not, now this is not just an eigenvector. This is the guy that gets sent to an eigenvector. It's like, well, that's fine. Now I just need to solve. It's like the guy that, this matrix, I want A minus 2i times my v2 to give me the v1 corresponding to this eigenvalue of 2. And so now you're just trying to solve the system of equations. So I wanted to come out to equal 1, 1, 1. I want the 1, 1, 1 to be here. I don't know what this should be. I know what this matrix should be. So just need to solve it. Yeah?
So 1, 1, 1 is v1, 2 or v?
Oh, sorry. This is for the eigenvalue 2. It's the first vector for the eigenvalue 2. So we have this chain, right? It's the first vector in this Jordan chain for the eigenvalue 2. And now we're trying to figure out what the second vector in the chain should be. But this is solving a linear system, right? We're really good at solving linear systems. We have this whole thing called linear algebra. Let's just do it, right? So let's do it. It's like one way to do this is you draw the augmented matrix. So we can draw the matrix -1, -1, 2, -1, -3, 4, -1, -2, 3. Time, and then on the right you put your goal, where you want to equals, and then you do row reduction on the left, and you kind of see like what happens. Are you familiar with this whole augmented matrix trick? So, I mean, it's just solving a linear system. Do it however you do best, but I guess I like this way. How are we doing on time? We got a couple of minutes, we can do this out. So, you know, maybe I'll use like this top guy, I'll just multiply by -1, to make it +1, +1, -2, -1. And let me use this to clear some things under it. So like I'll subtract this first row from the second row. That is, I'm adding this guy to the second row. So he becomes 0, -2, 2, 0, I think. Let me know if I did that wrong. I'm also going to add him to the bottom row. So that gives me 0, -1, 1, 0. Does that look right? And then you're like, oh, the last two rows are redundant, so you can always like subtract off one from the other to clear it. So I can clear these guys by subtracting off like copies of the last row from the first row. And well, you can keep playing around, but let's just think what this is telling us. This is saying like x plus y minus 2z is minus 1. And then this last guy is saying that just y equals z, right? Minus y plus z is 0. So y equals z. And so if I put that in up here, I'm getting that what satisfies the system of equations. It's like it's underdetermined, so it's infinitely many solutions. So just find one. Okay, I want y equals z. Let's make them both 1. And then if those are both 1, if these are both 1, I'm subtracting 1, so I want x minus 1 to be negative 1. So I think 0 works. Let's double check. If I multiply this first guy by 0, 1, 1, 0, 1, 1, that gives me 1, 1, 1. Yep, that works. So I can use this as, this can be my V2, 2. So now we found P. P is just this matrix that has as its columns these 3 values. That is, my P is just the matrix 0, 2, 1, 1, 1, 1, and 0, 1, 1. That's what my matrix P is. And so I guess you should try this out. You know, check that P times J times P inverse really does cover the original matrix A. And there's probably like a 70% chance that it will, because there's a good chance I made a mistake somewhere on the board. But in principle, if we did all the calculations right, it should. It will. OK, so now we've given a way to construct P. Well, we've almost given a way to construct P. For probably just about all the problems you'll see, like in an assignment, this will work fine. But there's one worry that you might have. And so let me just talk about that worry. Things can get a little bit more complicated, especially when working with larger matrices. So let me just talk about when this might fail. So I want us to imagine you're working with some 3 by 3 Jordan block. So suppose we have some 3 by 3 Jordan block, or bigger, 4 by 4, 5 by 5, a big block, right? Where lambda as an eigenvalue of A has geometric multiplicity, let's say at least 2, 3, whatever. So recall geometric multiplicity is the same thing as saying that the nullity of A minus lambda I is 2. The dimension of your null space is 2. That's what that's saying. That's saying that there are 2 linearly independent eigenvectors that correspond with lambda, not just 1 but 2. In this example, 1 only had a single eigenvector, and 2 only had a single eigenvector. Well, any span of the eigenvector, but the dimension of the nullity, the dimension of the null space or the eigenspace was 1. These were both eigenvalues with multiplicity 1. Geometric multiplicity. When I come over here, now let's suppose I have some lambda geometric multiplicity 2. So what does that mean? Well, it means what I just said. That means lambda has 2 eigenvectors, 2 linearly independent eigenvectors. And so now it's a little bit confusing, because here in the chain that we looked at, we had a single eigenvector, and then we just like bootstrapped our way up from it. But now the picture you should be having in mind is that there's not just one, but there's like 2 different eigenvectors, v and so I don't know what names to call these, but you know, like they're both trying to be 1, but you have 2 different ones, right? So I don't know if we call it 1 and 2 as competing by notation from before. Maybe you think both your v1 and your v2 are both just eigenvectors. They're both getting sent to 0. So under the map A minus lambda I, these both get sent to 0. And it's like, okay, but now I want to find some third eigenvector. And there's not a third eigenvector. This only has dimension 2. But I need to get a third guy, because this is a 3 by 3 block. So I need to find some like v3 over here. And it's like, well, what should I do? Should I like find the one that maps here? Or should I find the one that maps here? Or should I like try and do like something that maps to like some kind of linear combination of these two? Right? Like maybe it's not as obvious as before we trace the chain back. And so bootstrapping is becoming a little more complicated, right? You can imagine if you have lots of eigenvectors and you're trying to, maybe you have like 4 linear independent eigenvectors, but you want to end up with a collection of 7. It's like, well, how do I draw my diagram, right? So this is the worry. It's not a worry when you only have, a single eigenvector that spans your eigenspace, so your nullity is 1. But when you have eigenvectors of some nullity bigger than 1, and you're trying to get the rest of your guys to fill up P, this becomes a problem. And so the way we do it is we say, okay, forget the bootstrapping story. Instead, recognize. So instead, if we go back over here, say you just had like, I don't know, 3 of these guys. Then you could say that V1 is the thing that A minus lambda I gets multiplied by to give you 0. V2 is the thing that A minus lambda I squared gets multiplied by to give you 0. And V3 is the thing that A minus lambda I cubed gets multiplied by to give you 0, right? That's what this is telling us. That's what this diagram is saying. But you could also just summarize that all by saying, well, all 3 of these are solutions to A minus lambda I cubed times V is 0. That is, right, because if you already get to 0 by multiplying by him once, if you multiply by him 3 times, you'll still be at 0, right? So all of these vectors are just solutions to this. And so what V1, V2, and V3 really are is they're giving you a basis for the null space of A minus lambda I cubed. That's what they're really doing. Now, we had like found them one at a time and bootstrapped our way up. But if it gets kind of confusing how to bootstrap, you can just step back and say, really, this is what we're trying to solve. And so really what we're trying to do is instead, we're trying to just find, instead your V1 through your VK is just going to be looking for a basis for A minus lambda I to the K's null space. That's really what we're looking for. So this is exactly analogous to just finding eigenvalues, right? In general, if I'm looking for some eigenvalues, I don't know how many I have, V1 through whatever, I should give it some different letter than K, like through Vj, we're looking for some eigenvalues, eigenvectors. These eigenvectors will just be a basis for your eigenspace, which is the null space of A minus lambda I. Right? So here, when we typically do things, we have your eigenvectors given some lambda. You have eigenvectors which form a basis for your null space, and we call that the eigenspace. So your eigenvectors become a basis for the eigenspace. What we're doing here is we're generalizing a little bit, where they're not strictly the null space of A minus lambda I, it's that A minus lambda I to some power, because it's not necessarily going to be vectors that correspond to diagonal matrix, it's diagonal with these extra 1 things. But because of this analogy, we're going to call these vectors generalized eigenvectors. And they're forming a basis for this, which we'll call the generalized eigenspace. And typically you can do this just by finding, well, if there's just an if your eigenspace is just nullity 1, that is dimension 1, you can just find your first one, and then you can say, okay, now let me find the rest of the generalized ones in this way. But if your null space is something of dimension higher than 1, you can instead just solve this problem of, okay, let me look at this matrix, calculate it to whatever power, right? And then let me think about the null space. So let me find a set of all solutions to this times v equals 0, and then you'll get some collection of vectors that span that space, right? So you have the tools to do this. So sometimes you have this more general approach, but hopefully this kind of completes the analogy, right? We're trying to diagonalize a matrix. You can diagonalize a matrix if your null space has big enough dimension, but if your null space doesn't have a large enough dimension, we have to move to this generalized eigenspace. And here, this generalized eigenspace won't quite give you a diagonal matrix, but gives something pretty close to diagonal matrix, your Jordan canonical form. So I'll stop there today, but where we're headed next is we're going to see that now that we can do this, we can do some really cool things with matrices. Like we can calculate what is sine of a matrix, or what is e to a matrix, right? That's where we're headed. That's how we're going to cap things off next lecture.